Hello everyone. Thank you so much to Professor Prabha and Professor Pradeep for enabling my visit here. It gives me pleasure to talk to you about evaluating fault tolerant schemes for noisy hardware. Uh, this is some work that I did during my PhD and my postdoc time. Um, I'm I'm currently a senior scientist at Xanadu Quantum Technologies. It's a startup company based in Toronto, invested in building quantum computers using optical hardware. Before I go on to today's talk, I want to thank the collaborators that I had the opportunity to learn from. Some of them I'm still working with. In particular, these four for the purpose of today's talk. Um, the most important up top is David Pullen, my master's and my doctoral advisor, who very unfortunately passed away soon after I graduated from my PhD. Before going into today's talk, I want to tell you about my view of the field in three steps. Uh, it's divided based on the scale of systems we want to look at. So at the first, we have microscopic studies where we look at physical systems and we want to see how do we represent a qubit in this physical systems. So there are various candidates like superconducting qubits, trapped ions, NV centers, and so on. The next part of the next aspect is what if we have a handful of these qubits or physical systems, and here we are looking at intermediate scale studies, sometimes also called the NISQ era, and ultimately we want to solve real world problems. So here we are looking at large scale systems. In particular, we are looking at building large error correcting codes to do reliable quantum computation in the presence of noise, so do quantum algorithms, and so on. Much of today's talk is going to lie in the intermediate scale studies, where in particular we look at what happens when we study this scheme called quantum error correction beyond the theoretical paradigm of Pauli errors. Then I'll tell you about some fundamental problems that creep up in analyzing these theoretical guarantees of fault tolerant quantum computing while looking at realistic noisy devices. And then I'll end by discussing some recent work that led to efficiently diagnosing how these tools of quantum error correction would work on noisy hardware. Before we proceed, let's look at the problem at a very high level. As we all know, a quantum computer is nothing but an elaborate quantum circuit where the components are highly susceptible to noise. And what we want to ensure is that the effect of noise on the individual components, such as the qubits or the gates, does not manifest as an error in the computation result itself. What we do is we actually say that information should not be encoded into the individual systems. Instead, we should use collective states of many qubits to encode quantum information, which means that a logical quantum information, a unit of logical quantum information or a logical qubit is now a many physical qubit state. And this ensures that if some of the physical qubits undergo errors, then we can use an algorithm that's a quantum classical algorithm called quantum error correction to recover the information from these errors. Now, whenever we have a scheme like this, all we are worried about is what is the gain I get by increasing the overhead of my quantum computation, which is for every logical qubit, I've put n more physical qubits in the system. And these gains can be understood by plots of this nature, where on the x-axis, I have a physical error rate, and for every physical error rate that comes out of the device, I can map it to a logical error rate, which is the net error that persists in the logical information after quantum error correction. And the theory guarantees that if I use more and more systems to encode my quantum information, I get better and better suppression in the logical error rate. Now, the real question is, if I have a target that's demanded by some algorithm, then how much do I need to keep increasing the overhead? In other words, how big and big do I need to how big and big of systems do I need to consider to store my logical quantum information? And this comes to the central question, which is how much overhead and what quality of physical components are needed to achieve some target logical error rate. And that can be further distilled to ask, if I know all the parameters of my physical device, how can I use this to accurately predict what the logical error rate or the performance of a quantum error correction scheme would be? Before going into the actual details of how we answer this question, let me give you the answer itself, and then we can look into the details. Now, what we can naturally expect to do is, when we have a device in a lab, we can essentially mathematically model the device in some sense completely, and these techniques are called full process tomography. Once we have completely understood a mathematical modeling for the device, we can now simulate the entire quantum error correction as a quantum computation circuit on a classical computer to understand how much of a suppression of noise it can deliver in this scheme, which is done using numerical simulations. Now, we don't want to go that route because it turns out that extracting all the parameters is an unreliable process, and numerical simulations are hard, as you would expect. Instead, what we want to do is, we want to use some figures of merit or some quantifications of the strength of noise in the device to be able to accurately, with good confidence, say if this is the figure of merit, then this will be the logical error rate. Luckily, we have such figures of merit already defined for noisy devices. Some examples, or some popular examples, one of them is the diamond distance, which is popular in mathematical proofs. Another one is the fidelity. They have their own advantages and disadvantages. In particular, what we will see at the end of this talk is that neither of them are good at answering our problem, which is, neither of them tell us what the logical error rate would be in a quantum error correction scheme. Now, that being said, what we will also see is a new metric that we can come up with, which we call the logical estimator, which also measures the strength of noise in a device. And this logical estimator is tailor-made to answer our problem, which is, it tells us accurately what the logical error rate for a quantum error correction scheme would be. And then, using this as an operational tool, we will show how we not only study one specific error correction scheme, but we can also select one out of a few error correction schemes that is optimal for a given noisy device.
Sir, a question: when you say the fidelity is efficiently measurable and computable and there are experiments, you don't mean just doing tomography and
No. So, what I mean here is randomized benchmarking experiments to estimate the average fidelity of a device. So, it is efficient in the sense that it's not an exponentially scaling algorithm. Yes. Okay, so that was a quick glimpse of the problem and the result. Let's now go into detail at what the nature of this problem is and so on. So first, let's look at physical errors. As you all well know here, a quantum system interacts with its environment, and then we'd like to model this interaction as an effective dynamics on the system itself. And this dynamics is often called a quantum channel. Some examples of quantum channels are, when we think of the effective interaction as just probabilistically applying one of the four following errors, the identity, which is nothing, the X Pauli matrix, the Y Pauli matrix, or the Z Pauli matrix. Because these are Pauli matrices, they are called Pauli channels, and these models are attractive to do fault tolerance proofs because this is a classically inspired error model where we think of errors as occurring as probabilities. Some other examples for experimentalists, which is associated to something called the T2 time scale of a qubit, is related to another error model which is a quantum channel called the dephasing channel. And it's not just limited to Pauli matrices. We can also have energy relaxation in the system, and this is modeled as an amplitude damping channel, where after the channel the state, which is epsilon of rho, is expressed in that particular form. In general, it turns out that any function that preserves the structure of a density matrix can be a valid effective dynamics on the system, and these functions are represented by what are known as completely positive trace preserving maps, and they can be expressed in this sum form that we see here with some more properties on these operators. Now, whenever we say physical errors, we don't want to focus on a specific experimental device, but keep it general enough that can incorporate different noisy hardware. And for this reason, we want to consider a model of physical errors that is any general completely positive trace preserving map. So it's just any function that takes a density matrix to another density matrix. Now, what is it that we are looking for in these functions? These are complex mathematical objects, but what is it that we are looking is simply a figure of merit for this channel, which is some number that can tell me what is the strength of noise in this channel. So effectively, I'm looking for a number where it goes between two limits, and on one end I have a noiseless channel, on one end I have a maximum noise channel. Now, there are such candidates. One is called the diamond distance. So as you can imagine, a channel, basically you can think of it as an operation which takes as input the perfect state and gives us output the noisy state. So one can measure some sort of distance between the output and the input and characterize it as a strength of noise. In this case, it's the worst case distance. So it's the maximum distance between the input and the output for any input. That's the diamond distance. Now, sometimes it doesn't make sense to look at worst case. We can look at average case distance, or the average case distinguishability between the input and the output, which is called fidelity, or 1 minus that we often call infidelity. Because it's a channel, it's a mathematical object, we can look at different sorts of norms like L1, L2 norms, entropy of a quantum channel, its unitarity, and so on. Now, having all these different measures of noise strength, what we are looking for in a measure of noise strength is we are looking for a gold standard where we can use it in fault tolerance proofs. We want to measure it in experiments, we want to efficiently compute it, and we want it to answer our question, which is predict the logical error rate. Now, it turns out that if we look at these metrics and what qualities they have, all but diamond distance only the diamond distance can be used in fault tolerance proofs, whereas only fidelity can be measured. We can compute everything but the diamond distance, but what we don't know is if any of them can be used to predict the scaling or predict the logical error rate of a quantum error correcting scheme. So we saw what physical errors are, and we saw how to quantify the strength of noise, and we saw what we are looking for in this quantification, which is we want this quantification to give us a good estimate of what the logical error rate would be. Now we keep saying logical error rate, let's go in and see what is that logical error rate. So we know that we cannot encode information in just single qubit systems because they're susceptible to noise. Instead, what we do is we encode information in systems of many physical qubits, and operationally it's done using a circuit, a unitary circuit called an encoder. At the end, what we have is we have a one-to-one mapping between every state row and every output of the circuit. And then this is the state of the quantum computer when it starts, and then it undergoes noise. In this simple form, we'd like to think of noise as affecting the qubits independently. And once there's noise, we want to correct this noise. So what we do is we first do a set of measurements to detect errors, and conditioned on those measured values, we apply some correction. So here we call these measurements syndrome measurements, and then conditioned on these measurements, we can apply some recovery. Here one can think of the recovery as being general, but for implementation reasons, we can think of the recovery itself as being something that's easy to apply, because we don't want to apply a complex circuit to correct the noise. And then, because after the recovery, we should with good confidence have what we had right after the encoder. So we can imagine extracting the information that we initially intend to encode, and like this we can black box this whole operation and say that I input a quantum state rho, I should most of the time get the output as the state I input, which is rho. But if the system fails, then I would get a different state, rho prime, at the end. And this means that I can now look at the entire process as another noise channel, which takes us input rho and gives us output rho prime. And this is a nice tool, because now I can forget about the fact that there's quantum error correction in the middle, and just call it an effective channel, where the effective channel denotes the combined effect of noise plus quantum error correction. And now I can...
Here you're assuming still that your encoder, decoder are all ideal.
Yes, we are assuming that there's no noise in the quantum error correction procedure itself, for simplicity.
And is it like in the picture that you assume that the noise only acts
Ah,
after the encoder?
yes, so in this case, yes, we model the imperfect encoder as the perfect one followed by some noise. Yes. But this noise is not restricted to be independent and identical across qubits. We can in general have entangled noise, but the efficiency of computing the effective channel will reduce if we have complex noise systems. Now, the reason we define this effective channel is now we want to compare it with a physical channel, and then we want to see how much noise is there in the effective channel versus how much noise is there in the physical channel. Now, as an aside, we said that whenever we do quantum error correction, the logical error rate is suppressed. If we want more and more suppression, what we can naively imagine doing is we can imagine doing this encoding again and again and again, where we have one logical qubit encoded in n physical qubits, and we can encode each of those n physical qubits again into n physical qubits, and so on. And this means that each time we re-encode, we get more and more suppression on the logical error rate. And like this, we can consider schemes where we encode one logical qubit in n to the L physical qubits for L layers of this process. And this in general is called a concatenated code. Now we can use our abstraction technique again to study these codes, because as you saw, whenever we had error correction, we can abstract it into an effective channel. So in this case, we can look at it as an effective channel on each of the physical qubits in the concatenated code, and like this we can start from the bottom and basically compute the effective channel for every layer of concatenation. And like this, we have an effective channel for the concatenated code. So now we not only have an effective channel, we have an effective channel that we can design to achieve any kind of suppression on the logical error rate. And now we want to study what properties of the physical channel correlate with properties of the effective channel. So so just as an illustration, what we want to study is we have physical channels, and we use some numerical technique which I won't go into, which is detailed here, to compute the effective channel for a concatenated code. Once we have the effective channel, we can study its noise strength according to the different measures that we saw. And what we want to study is before quantum error correction, I have physical channels with different parameters of noise strength. After quantum error correction, I can use any of these to quantify the noise in the logical channel. And I want to see what parameters there correlate with parameters here. Because fidelity is interesting and can be measured in experiments, let's take the example of fidelity to represent the logical error rate. So, we are almost done setting up the problem. We want to ask, if I have a device whose noise strength according to infidelity or diamond distance or any of them is say 1%, I want to know, can this tell me the logical error rate? And we'll find out if it can. So, we want to basically show our answer using plots of this type, where every point here represents one valid hardware device, which is some valid completely positive trace preserving map. Now what its x-axis is saying is its physical noise strength according to any metric that we want to choose, say fidelity or diamond distance. What its y value is telling us is its logical noise strength according to the logical fidelity. And what we are looking for is, we are saying, if I only know the diamond distance of the physical device, can I predict what the logical fidelity would be? So in this plot, if I know what device it is, I know which point to look at. But if I don't know what device I'm looking at and I know only this figure of merit, I only know what vertical cross section to look at. This means if there are several points or several devices with the same measure of physical noise strength, then just with the measure of physical noise strength, I cannot say what the logical error rate would be, because different maps would have different logical error rates. So what we don't want is a vertical spread here. Let's see what happens with diamond distance. Unfortunately, what happens is that if we look at all different types of noise processes that can happen at the level of a qubit, we find out that at a given diamond distance, there can be a lot of physical noise processes that have the same strength of error according to the diamond distance, but they have vastly different logical error rates. In this case, if I look at different noise processes at a strength given by the diamond distance equals to 10%, it turns out that logical error rates can vary over 8 orders of magnitude. And for the experts, if you look at, if I only know the diamond distance and I have to think of quantum error correction, what is the worst device that I have to be prepared for and what's the best device I can hope for? It turns out that the worst device is something that has decoherent errors, and the best device is something that has unitary errors or calibration errors. Now let's look at fidelity. It's a similar story for fidelity, where if I look at devices at some fidelity noise strength, let's say 93% here, there's a vast variation in the logical error rates. And now if I ask, if I only know the fidelity of a device and I want to know what is the worst and what is the best for a quantum error correction scheme, it actually reverses, in the sense that if you only know the fidelity, the best you can hope for is decoherence, whereas the worst you should be prepared for is coherent or calibration errors. So my point is that the error metrics not only are unable to tell us with good confidence what the logical error rate is, they are unable to also reproduce to us what the best and worst case scenarios would be. Okay, so this along with other metrics led to the conclusion that neither of these parameters, these standard error metrics, so as we say it, can be used to give us an accurate prediction of the logical error rate. Now, in the remaining of this talk, I want to show you some attempts at coming up with a new figure of merit that is engineered to give us a better prediction of the logical error rate. Here, before we go around and find a new figure of merit, we want to use a twofold strategy. First, we want to say that errors can be very complex in nature, whereas the simple model of errors is Pauli errors, where we only think of the 4 possibilities which are given by the Pauli matrices. So, the natural question is, can we reduce the complex model to the simple model for our analysis of quantum error correction? And it turns out that there is a technique to tailor generic noise processes to an effective Pauli noise process that affects the system, and this technique is called randomized compiling. The second part is that now that there's only Pauli errors occurring, we want to understand the different parameters in this Pauli error model, which is the different probabilities of the Pauli errors. This can be extracted in experiments using something called noise reconstruction. Now, once we have the different probabilities of Pauli errors, the last ingredient here is to use them in an efficient way to approximate the logical error rate itself, which is what we want to predict. And this we achieved for the class of concatenated codes. And this efficient approximation is what we call a new error metric, and we called it logical estimator. This 3-step process now leads us to an efficient diagnostic tool for quantum error correction. So let's look at each of these steps. Let me give you an idea of each of these steps by what we mean by taking a complex noise process and tailoring it to a simple noise process. Now, it turns out that if you look at a completely positive trace preserving map, it's a function that maps any density matrix at the single qubit level to another density matrix. Now, as you know, Pauli matrices form a basis for 2 by 2 Hermitian matrices. So, we can look at a density matrix as a vector where each component corresponds to a Pauli matrix. So, any transformation is basically some 4 by 4 matrix on this vector space. Now, because we are not looking at any transformation, we are also looking at those that preserve the density matrix properties. It turns out that instead of 16, we need 12 independent parameters to specify a general quantum channel on 1 qubit. What randomized compiling does is that it's an experimental technique to essentially do transformations, effectively reduce the noise parameters that are important for quantum error correction from these 12 to just 4 of them. And in this representation, we are essentially removing the off-diagonal parts of the noise and retaining only the diagonal parts. Noise reconstruction is a method to estimate each of these diagonal components with some confidence. So at the end of these two techniques, we have a simple noise model that only applies Pauli errors, and we also have the relative probabilities of the different Pauli errors. Now, I want to tell you a little bit on how randomized compiling actually works. What it prescribes is that if we have a circuit where the elements are undergoing complex noise processes like general CP, completely positive maps, it uses the mathematical argument that if you take a general process and you apply a random Pauli matrix to the input and undo that Pauli matrix at the output, and look at the average over all such randomizations, what it will turn out is that the process itself on average behaves like a Pauli channel. We can use this argument on every element of the circuit here. So what we can do is take our quantum algorithm and put random Pauli gates before and after every component in such a way that the net effect does not change of the circuit, and if we now average over all such randomizations, the average circuit behaves as though there's only Pauli noise in the original circuit. What we did was we elevated this technique to the quantum error corrections case, where we have a logical circuit with quantum error correction at different gaps between the circuit. And now we can imagine inserting random Pauli gates before and after every component. And now we can do this at no extra cost, because these random gates can just be absorbed into the quantum error correction procedure itself, where we say that I have to apply another gate in effect, so I will correct it only up to that extra gate. And like this, we can guarantee that the effective noise that we need to accurately predict the logical error rate for is just a Pauli error model, whose relative probabilities of Pauli errors we can efficiently extract. Now, the last piece of the puzzle is, if we know the probability of the different Pauli errors, how do we efficiently compute the logical error rate? Now, if there are only Pauli errors occurring in our scenario, all we need to see is which of these errors are corrected by the code and which of these are not corrected by the code. Because those that are not corrected by the code will manifest as errors on the logical information. Now, to compute the total probability of uncorrectable errors, all we need to do is look at every uncorrectable error and add its probability. Now, as you would expect, it's in general not possible, because it will turn out that for a code on n physical qubits, there are an exponential number of uncorrectable errors. But because we want to restrict the study to concatenated codes, it turns out that due to the nice recursive structure of this encoding process, we can efficiently estimate the total probability of uncorrectable errors for this entire code if we know the total probability of uncorrectable errors for each block. Because every element, this code can be seen as several replications of one level at the successive levels. In particular, what we can observe is we can now look at the concatenated code as a tree-like structure, where at every step in the tree, we are doing something that we would do in the entire tree. So, we can write the total probability of uncorrectable errors as uncorrectable errors in a block plus uncorrectable errors that come from earlier blocks. And this neat recursion structure can be solved in time that is linear in the number of layers, because each time we add a layer, we add a level to the recursion. And this means that if we look at how it scales in the number of physical qubits, which is the total number of nodes at the end of the tree, it actually scales polynomially. And this guarantees that our approximation of the logical error rate is not only efficient but is also accurate. And like this, we have an accurate and efficient approximation to the logical error rate, which can be constructed out of experimental data. And this is a good characterization of the noise strength in the physical device, particularly because it is also giving us a value that's close to the logical error rate. Now, I want to show you how good this is in practice. So, let's go back to our problem of looking at how bad the fidelity as a metric was, and let's compare it with this new metric, which is the logical estimator. Now, we have a plot with two colors just to compare two different metrics, one fidelity and another logical estimator. If we look at the top axis and the spread in the gray dots, we are looking at the spread in the logical error rates across devices of constant fidelity, and you see that there is a finite width in the vertical cross section. Whereas if you look at devices of constant logical error rate, which is the graph in red, and look at the different logical error rates across those devices, the spread is very less, which means that if I knew the fidelity about a device and nothing else, my confidence of the logical error rates would be the width of this gray region, whereas if I knew the logical estimator and nothing less, my confidence in the logical error rates would be the width of the red region, and here we see that the logical estimator can give us a more tighter estimate of the logical error rate. It's similar with the diamond distance except a little more dramatic in the sense that if I knew the diamond distance and nothing else, my estimate of the logical error rate would span across a few orders of magnitude, whereas if I had access to the logical estimator, I would be extremely sure about the logical fidelity. With this, we want to show some instances that are evidence to the fact that logical estimator is a much better predictor of the logical error rate as compared to the standard error matrix. Now, it's nice. Yes, yes.
So the technique hinges on the fact that your Pauli's form a basis.
Yes.
And also on the fact that you can twirl, that you apply
Yes.
random Pauli's.
Yes.
So suppose I pick a different error basis.
Yes.
Let's say it's a unitary error basis. Would that also work equally well? Because there are nice unitary error bases.
So it would work really well if the twirling with respect to that basis gives us a stochastic error model, because the last part of this technique is essentially about counting the Pauli errors on which the code fails. So this means that we are looking, it relies on these errors occurring with different probabilities and the logical error rate being a sum of probabilities of the failure cases. So if we twirl with a different basis and we get a stochastic error model where we can say the total failure probability of the code is a sum of failure probabilities of the individual errors, then this will certainly work.
So you're referring to the fact that you get a depolarizing channel if you twirl.
A Pauli channel, yes, exactly.
The reason I'm asking is if you pick a basis like say identity Z and a raising operator and a lowering operator,
yes,
that would form a basis.
Yes.
And it might capture error models like amplitude damping and generalized amplitude damping, maybe model them closer than the Pauli's would do.
Yes, yes.
Yeah.
The resulting channel would not have a stochastic description, which would counter with this technique, but it would still be interesting to see if we only care about counting those Krauss terms on which the code would fail. So what I want to show you at the end is that one of the other uses of having an efficient technique to predict the logical error rate is to now quickly be able to say which quantum error correcting scheme would be better suited for a given hardware platform. Because if we did not have the logical estimator to answer the same question, the only answer lies in actually testing it in a numerical simulation, which is intensive, and that can only reveal which scheme is better. So here we want to take an example where, let's say, we had 7 qubits or concatenations of 7 qubit codes at our disposal. There are 2 choices here and it's unclear which one is better. One is called the Steen code and the other one is called the cyclic code. Don't bother if you don't know exactly what these two are, just that they are different strategies of encoding. Now let's say we have an error model, a noisy device, which we took from this article here, but it doesn't matter. The model of noise here is that with some probability PQ, we apply a rotation about the Pauli axis Q on the qubit. And then we have a tunable parameter eta, which we can increase or decrease to vary the strength of noise. And here all we are varying is the relative probability of Z and X rotations. So this is a complicated hardware device, and the real question is, to combat this type of noise, should I use the Steen code or the cyclic code if I know the value of the tunable parameter eta? One thing that I could do is for every value of eta, I can take this noise process and completely simulate the quantum error correction algorithm. It would be an exponential time scaling simulation and compute the logical fidelity. We obviously don't want to do that. But if we did that, the results would follow this dashed line where we see that for a specific regime of noise given by eta, the Steen, which is the blue, has a lower logical error rate than the red, which is cyclic, which means in that regime of eta, it is better to use the Steen error correction scheme, and for a higher value of eta, the cyclic has a lower logical error rate, and this suggests that it's better to use the cyclic scheme for that higher value of eta. It's important to know that because otherwise we would be suboptimally using one of the two schemes. Now, we want to arrive at a similar answer in a much more efficient way, and therefore we want to use the logical estimator as a proxy to the logical error rate itself. And here we see that if we did the same sort of analysis without computing the logical error rate but just quickly computing the logical estimator, we arrive at a similar conclusion in the sense that the logical estimator also points out the region of crossing where one code becomes better than the other code. And this is an illustration to show that a good use of the logical estimator is also to select the better error correcting code for a given noise process. Okay, so hopefully I've told you the importance of the question where given some properties of the hardware device, we want to say what the logical error rate would be for an error correction scheme, and one of the answers here is to compute a property that we call the logical estimator. And I just want to end by pointing out a few interesting future research problems. So one of the future research problems that we looked at partially was to go beyond concatenated codes and compute these useful logical estimators for topological stabilizer codes, in particular surface codes and color codes. And because there's an interesting decoding technique for surface codes that assumes that the surface code has a concatenated structure, these are called renormalization group based decoders, we extended some of this work to surface codes also. There's an interesting question here, which is when we use noise reconstruction to extract all informations about a device, can we use this to further make quantum error correction itself better, because now it will be tailored to the device. Another interesting question is when we do randomized compiling, we are actually taking a complex noise process and simplifying it to Pauli errors. But is it really getting rid of noise, or is it giving us an equivalent Pauli error model with actually more noise in it? And we looked at this question and we proved that for specific cases of physical errors, which are coherent errors or unitary errors, we actually get better logical fidelities by just applying randomized compiling. But for some other cases of errors, we pointed out instances where randomized compiling removes noise sources but actually gives worse logical fidelities. And we are looking at noise tailoring methods to yield decoherence free subspaces and so on. And I want to kind of end by putting it into the larger perspective and say that I'm more happy to talk about the other aspects also, which is microscopic studies, where I have some knowledge on working with continuous variable encodings for qubits, and on the large scale studies on surface codes and linear time decoders for model of errors called erasures and also computational complexity problems with respect to quantum error correction. And with that, I'd like to end and open it for questions.